Our project is large-scale multi-label text classification, which has many practical applications, including to determine the categories of new wiki page. This problem is challenging because the data is very sparse, which makes it hard to predict label accurately. Another challenge is the computational cost because the dimensions for both features and labels are huge. In our project, we will focus on embedding-based and deep learning method. We implement two existing methods and finally combine the two types of method. The first existing method we implement is called sleek. The key idea is to map sparse label vectors into label embeddings. This is learned by keeping only the pairwise distances among nearest neighbors, and the regressor is trained to predict from features to embeddings. To make it scalable, pre-clustering is implemented for large dataset.
The state-of-the-art CNN model is XML-CNN. It first trains an embedding layer and then uses filters with different sizes to build the count layers. Filters only move along the word sequence to get the meaning of the sentence. Also, it uses sigmoid cross-entropy laws for multi-labels. We use random forest as our baseline and implemented both sleek and CNN models. We modified the CNN model by using pre-trained word-to-vec and increasing the complexity of the model structures. We also proposed a new model, combined CNN with sleek. For evaluation method, we used precision at K and F1 score, which is rarely used in other papers. One of the drawbacks of CNN is that it still needs to compute and store the large multi-hop label matrix. Thus, we propose to use the reduced embedded labels output by sleek as the target of CNN. We hope it can increase the CNN training speed without compromise of the accuracy. Since sleek embedding needs huge memory, we first cluster the samples and then run CNNs on each cluster.
This figure shows the evaluation metrics for the small-size BibTeX dataset. The solid lines show the results of our final model, which is tuned based on the criteria of reaching both large precision at case and F1 score, and it can be learned that best precision at case may not be the best choice when tuning models and may not be sufficient to evaluate the model. It can be learned from the overall results that CNN models outperform others in precision at case. However, the F1 score is much lower than the sleek model because the recall is low. In contrast, the sleek model reached a higher F1 score because the recall is much higher, but it has many false positives which results from the KN label reconstruction method. When comparing memory usage, CNN outperformed others a lot. The red memory values in the table mean that we got memory errors which cannot be solved even after pre-clustering and using powerful Google Cloud machines. We got the results by running our models on a subset of smaller clusters, which spans about 60% of the original dataset. The results for our combined model is very unstable, which may result from the CNN overfitting problem. The evaluation metrics drop after first 1 or 2 epochs. Another reason could be that the sleek label reconstruction method is not compatible with the CNN model.
In all of the CNN models, high precision at 1 is achieved very quickly, but P at 3 and 5 are improved gradually during training. Models with multiple filters, the more complicated CNN structures, achieved more stable P at K. CNN models has very low F1 scores and recalls compared with sleek models, which means it's hard for CNN to catch all of the labels. This might be caused by the high label density in wiki dataset. Again, model with multi-layers has the best performance of precision, recall, and F1. Here are our conclusions.